Hunting for a Studio 5000 download? Here is the honest picture. Studio 5000 Logic's Designer is Rockwell Automation's commercial IDE. It is not free. The base license runs several $100s per year for a single seat. You need a Rockwell account and a valid subscription to activate it. There is a trial path. Rockwell offers evaluation licenses through their sales channel and certain academic programs, but it requires registering with Rockwell directly. The trial is time-limited and hardware-locked to a single machine. There is no anonymous download. The full guide, linked below in the description, covers every legitimate path. The trial request process, the free emulated controller option, and what the license tiers include. That link goes to the Studio 5000 tutorial page at plcsimulationsoftware.com. Now, what this video gives you is the ladder logic itself. XIC, XIO, OTE, OTL, OTU, the TON timer with the timer done bit. Every instruction the AB dialect uses. You will build a start and stop motor rung from scratch, instruction by instruction. Practice every rung right now in the browser at plcsimulationsoftware.com. No install, no license, no Rockwell account. Start with XIC. XIC stands for Examine If Closed. In Allen Bradley ladder logic, the name refers to a bit state in the PLC tag database, not the physical state of a field device. XIC evaluates true when the bit it is examining is set to 1. That is the closed state in ladder logic terminology. Think of it as, is this bit on right now? The bit could be driven by a push button, a proximity sensor, an internal flag, or a timer output. If the bit is 1, XIC evaluates true. Current flows through the contact to the right. The confusion begins with physical wiring. When you wire a normally open push button to an input card, the input bit is 0 at rest and 1 when pressed. An XIC on that input goes true when the button is pressed. That matches your intuition. But when you wire a normally closed push button, the input bit is 1 at rest and drops to 0 when pressed. Stop buttons are typically wired normally closed for safety. Now an XIC on that stop input is true at rest and false when pressed. The instruction examines the bit state, not the mechanical configuration of the field device. This is the source of almost every XIC versus XIO confusion in AB programming. That brings us to XIO. XIO stands for Examine If Open. It evaluates true when the bit it examines is 0, the open state. XIO on a bit evaluates true when that bit is off. Here is the gotcha that trips up every new Allen Bradley programmer. A normally closed stop button, wired correctly to the input card, gives you a bit that is 1 at rest and 0 when pressed. To use this in a start and stop rung, you place an XIC on the stop input tag, not XIO. The bit is 1 at rest. You want the rung to pass current at rest. You need a contact that is true when the bit is 1. That is XIC. When the stop button is pressed, the bit drops to 0. The XIC evaluates false. The rung drops. The motor stops. This is counterintuitive because the physical push button is normally closed, but the instruction you use is XIC, not XIO. XIO is for when you have a normally open field device and you want rung continuity when the device is at rest. That is uncommon in motor control but appears in interlock logic. The rule of thumb: think about the bit state in the tag database, not the physical configuration of the device. What is the bit when the device is at rest? If it is 1 and you want rung continuity at rest, use XIC. If it is 0 and you want rung continuity at rest, use XIO. The output instruction for most motor control rungs is OTE. OTE stands for Output Energize. When a rung evaluates true, OTE sets the output bit to 1. When the rung evaluates false, OTE resets the bit to 0. It is not a latch. It is directly tied to rung continuity. Now build the standard 3-wire start and stop motor rung, instruction by instruction. Place an XIC on stop_PB. This is your normally closed stop button, bit 1 at rest. Place an XIC on start_PB in series. This is your normally open start button, bit 0 at rest. Place an OTE on motor_contactor. When stop is 1 and start is 1, the OTE sets the contactor bit. But the moment you release the start button, start drops to 0. The OTE resets. The motor drops. That is not a working start and stop circuit yet. Add a parallel branch to the same rung. Place an XIC on motor_contactor in parallel with start_PB. This is the seal-in contact. When the motor starts, motor_contactor is 1. The XIC in the parallel branch is true. Even after start drops to 0, the parallel path keeps the rung energized. The rung is latched. The motor runs. Pressing stop drops stop_PB to 0. The series section goes false. Rung continuity breaks. The OTE resets. The contactor drops. The seal-in contact opens. The rung delatches cleanly. That is the complete 3-wire circuit in AB ladder logic. The shared LadderRung component in the browser simulator animates every stage. Placing the contacts, closing start, watching the rung energize and the seal-in latch, then pressing stop. 2 more output instructions you will see in Allen Bradley programs, OTL and OTU. OTL is output latch. OTU is output unlatch. Unlike OTE, which resets when the rung goes false, OTL holds its bit at 1 even after the rung drops. The bit stays set until an OTU instruction on the same bit evaluates true. This is the Allen Bradley latch coil pair. You see them in conveyor and sequence logic where a state should persist regardless of what the triggering rung does next. The critical difference: an OTE coil goes false the instant its rung goes false. An OTL bit stays set until explicitly cleared by OTU. A common mistake is using OTL for a motor run bit when the programmer wanted self-latching OTE behavior. The motor would never stop because no OTU rung exists. Use OTL and OTU as a matched pair, always with both rungs present in the program. The TON instruction is Allen Bradley's on-delay timer. TON stands for timer on delay. When the rung enabling the TON is true, the accumulated value climbs from 0 toward the preset value. When accumulated reaches preset, the timer done bit sets to 1. The done bit is called DN. The DN bit stays set as long as the rung is true and accumulated equals preset. When the rung goes false, the accumulated value resets to 0 and DN clears. In the AB dialect, the timer is a tag of type timer. The preset and accumulated are submembers. The done bit is the tag named.dn. So if your timer tag is motor_delay, the done bit is motor_delay.dn. You use an XIC on motor_delay.dn to trigger whatever follows the time delay. The browser simulator's AB dialect mirrors this exactly. Timer tags, preset and accumulated submembers, and the .dn done bit. You can build, run, and watch the accumulated value count to preset and the DN bit set in real time. Practice rungs for all 3 timer types are in the AB dialect track. Find it at plcsimulationsoftware.com/learn/dialects/AB. A word on what the simulator does and does not replicate. The AB dialect implements XIC, XIO, OTE, OTL, OTU, TON, TOF, CTU, and the standard coil types. The programming model is genuine ladder logic, rungs, rails, power flow, energized states. What it does not replicate is the Studio 5000 IDE, the interface, the project tree, the I/O configuration, the controller properties. The value is practicing instruction semantics and logic patterns. These are the concepts that transfer directly to real hardware regardless of which IDE you use. When you sit down at Studio 5000 for the first time, XIC versus XIO behaves exactly as you practiced. The 3-wire motor rung, the OTL and OTU pair, and the TON done bit all behave exactly as you practiced them. The IDE is a wrapper. The logic is the substance. Start with the free AB dialect lessons at plcsimulationsoftware.com. The Studio 5000 tutorial page, linked below, has the full lesson path alongside the guide to getting a legitimate Studio 5000 trial. If this cleared up XIC versus XIO, or why your stop button uses a normally open instruction, subscribe. The next video covers TIA Portal beginner programming with the same pattern. Real instructions, real practice, no install. See you there.